All right, welcome everyone. We are thrilled to have a panelist of experts with us today, both from our team and externally, to really talk about RSC and utilities and our ANAGRAM model with how utilities get the most bang for the buck in reducing risk. I'm going to let Max Henrian start off and kind of introduce our awesome group that we have here today. And again, if you guys have questions, please chime in. We love your participation. Drop that in the Q&A or the chat and raise your hand and we'll get to you shortly. So with that, I will let Max take it away.
Thanks so much, Mitsu. Really appreciate the introduction. So we're going to be talking about, the subtitle, which is not shown here, is risk spend efficiency, which is kind of a technique that some utilities are using to figure out how to get the most bang for the buck in terms of reducing risks. And I'm going to speak first for a few minutes and then introduce my colleague at Lumina, Ben Filstrup, who's one of our top modelers and analysts, to give a demonstration of our ANAGRAM software. And then we're very fortunate to have Sam Savage, many of you might know, the author of The Flow of Averages and his new book, Chantification, which to talk about dealing with uncertainty in RSC. And then the late addition that was not really advertised, I'm pleased to welcome Ernest Beaver, who is Director R&D in the Hydrogen Center at GTI Energy, which some of you might know formerly was called the Gas Technology Institute, that has been working with us. So most people, at least until recently, most of us who, at least those of us who don't work for utilities or regulatory agencies and so on, tend to take electricity and gas and gasoline for granted. We switch on the light and the electricity flows, we light our stoves, we fill our cars with gasoline, and well, I guess most recently maybe we think a little bit more about the prices than we used to. But in the last few years, especially in California, but also in other places, we're starting to realize, even those not in the industry, that there are some significant risks associated with these modern conveniences. And although some of you might be well aware of them, others, I think it might be useful to just do a reminder of what we're talking about in terms of the threats, or at least a few of them, before we get into like, how do we deal with them? So those of us living in the San Francisco Bay Area Peninsula might remember the 2010 San Bruno gas explosion that killed 8 people due to defective welds that were installed, over 50 years ago in a gas transmission pipeline. Second one was the massive gas leak from the storage facility in Aliso Canyon over 2015 to 2016 that released over 100,000 tons of natural gas into the atmosphere. And perhaps, well, almost certainly the most horrific recent incident was the Camp Fire in 2018 that I'm sure all of you are very well aware of, that almost entirely destroyed the town of Paradise and killed 85 people. So for those of us in the audience that might not be in California or might not even work for utilities, I thought I'd include one other example for a pipeline utility, Colonial Pipeline, which delivers 45% of the fuel consumed on the US East Coast. As many of you might remember, last May, the pipeline was shut down for a week due to a ransomware attack. And causing a spike in the price of gasoline. Maybe looking at from this perspective, the spike wasn't all that horrific, but it seemed so then. Colonial Pipeline paid the hackers $5 million in Bitcoin to get a decryption key. Interestingly, the decryption key, it took so long to apply the decryption key, it turned out to be faster to get most of their data files back from backup rather than decrypt them. And the FBI, as you might have heard, managed amazingly to retrieve most of the ransom payment. Apparently, Bitcoin is not quite as anonymous as we thought. Although, since due to the crash in the value of Bitcoin, the value that they received was considerably less than what they'd paid. So these are just kind of a few most noteworthy examples. So part of the problem for a utility, or really any kind of organization that's trying to mitigate risk, is, and I'm going to use right now a cyber threat example. There's a whole set of different kinds of risks that give a headache to the risk manager. Here are some of the cyber threats, just a few of them. Well, fortunately, we also have a bunch of controls, or what we might call mitigations, different things that we can do that will mitigate, reduce, avoid some of those risks. But, this is sort of a solution, but it creates more headaches for the risk manager. Which of these do we select? What are most cost effective? We can't do everything. And, in the utility, non-cybersecurity space, here are some other examples. The risk of wildfire ignited by power lines. There's public safety power shutoff, where we switch off the power when the wind is blowing and the vegetation is dry in certain areas to reduce the risk of fire. Obviously, that has costs as well as benefits. Perhaps a simpler one, enhanced vegetation management, is cutting back the vegetation to reduce the chance that a branch might fall into a line. Covered conductors, putting covering on the conductors to minimize the chance of ignition, or, bury lines underground. In the gas area, there's a whole set of mitigations. This is just some of them. I'm not going to go through them all in detail, but the example that Ben will be showing you in a moment will illustrate a few of these mitigations for gas transmission line risks. So what do we do about all that stuff? Well, one more bad example, horrific example, but just to underline the issue, was last year the Dixie Fire that burnt a massive area in California. Really, who would want to run a utility company in California or anywhere in this era? Well, one person that heroically stepped up to it, beginning of last year, is Patty Poppe, now CEO at PG&E, who a week into the Dixie Fire announced plans to bury 10,000 miles of power lines underground at an estimated cost of $20 billion, which seems like a nice solution. Will take probably 10 years or more. Turn, which represents one of the organizations representing ratepayers, complains that that cost might not be worth the benefits. Well, how do we make those decisions? I mean, that's really the challenge. And about 6 years ago, the California Public Utility Commission developed this risk decision framework, developed in conjunction with the investor-owned utilities and ratepayer organizations like Turn. And it requires them to perform quantitative risk analysis on the key risks, identify what mitigations potentially could reduce those, and quantify their effectiveness. And submit RAMP report, risk assessment mitigation phase, every 3 years as part of our process of being public about their risk management approach, and also to get approval from the CPUC that they're making the investments in the most cost-effective ways. And this framework requires that they use this metric called risk spend efficiency as a guide to selecting the mitigations. And by risk, risks have a variety of attributes, including not just safety, potential fatalities, but also reliability and of course, cost. So these all need to be put together in a quantitative framework. And I'm only going to describe those very briefly. First, how do we define and calculate risk spend efficiency? This is the only slide that has a few equations on it, but hopefully you'll find them pretty simple. So this is a pretty standard way to define risk as likelihood of an event times its consequence, magnitude of consequence, if you like. And then after you apply a particular mitigation, the risk is perhaps reduced. So the new risk is the old risk times 1 minus the effectiveness of the mitigation. This is a way to define effectiveness. And then the risk spend efficiency, RSE, of a mitigation is the ratio of the risk reduction, the change in risk from before to after you apply the mitigation, summed over all the different events that would be affected by the mitigation, the risk events, divided by the cost of the mitigation. Or equivalent, you can just say it's the risk times the effectiveness summed over the mitigation, the events and effects divided by the cost. So the basic concept is really pretty straightforward. What makes it a little bit more complex is that we have to deal with these different attributes. And the risk decision framework right now requires a multi-attribute value function. And this is kind of an overview example of how. So the framework requires that at least they consider safety, reliability, and financial cost, optionally other attributes. And for each one, there's some natural units, fatalities for safety, customer minutes interrupted for reliability, and a lower and upper bound for each attribute. Now, this is for a particular utility. Let's say the worst possible thing they can conceive is 100 fatalities, 2 billion minutes customer interrupted, and $5 billion. So let's say a particular risk has 20 fatalities, 500 million CMI, 500 million cost. So the multi-attribute value function is designed to create a single risk score combining these things. So we look at, for each of these, what is the percent of this value within the range between lower and upper bound. And then we apply a scaling function that takes the percentage range into a score between 0 and 100. Some of the scaling functions are non-linear. They can be linear at the choice of the utility. And then you get a scaled score out of that, multiply each by a weight, and sum the weighted scores together. So those of you that are familiar with decision analysis, this is a fairly typical kind of approach. There's a few wrinkles here. Sam and I are actually part of a group of consultants that are currently making comments on how the utilities are using this framework for the CPUC. But we're not currently, we're just going to be talking about what the utilities are currently doing. This isn't the time to mention any of our comments already. Those will be becoming public later on this year. So if you compute RSE for each of a set of mitigations, again, I've gone back to security example, this RSC curve is a way to help prioritize them. So we're plotting the cumulative reduction in risk on the vertical axis against the cumulative cost. And then each of these things is a particular mitigation project. And we've ordered them by decreasing RSC. It turns out that on this kind of graph, the slope of each line segment indicates the RSC. So if you order them by decreasing slope, the way we've done here, you start out with the most cost-effective ones according to the RSC. And then let's say you have a budget of $120 million in this case, then we'll do all the ones here that fall within the budget up to cyber insurance, but penetration testing is outside the budget. These numbers are illustrative, it's kind of fictitious in this example. Ben will be showing you an example that looks like this for gas transmission pipelines. So I'm going to now hand over to Ben Filstra. Ben is my associate at Lumina, who's been helping develop ANAGRAM, Analytica Gas Risk Assessment and Management tool, which is a software tool implemented in Lumina's Analytica software that we've developed for a large gas utility. And although the numbers that you'll be seeing here are all fictitious, obviously we can't share the real numbers, but to illustrate how this approach to risk management can be applied in a very practical way to a very important decision. So Ben, take it away.
Thanks. Can you verify you can see my screen?
Yep.
Fantastic. Thank you, Max. So as he said, my name is Ben Filstrup. I'm an associate consultant at Lumina Decision Systems and one of the main developers of this tool we call ANAGRAM. To quickly preface some key information, this is a system in use by a large gas utility. As Max just said, the data is all anonymized. And when we talk about mitigations, we're talking about mitigating specific threats. So if you turn your attention to this table down below, you can see some of the different threats we talk about mitigating. So for example, if you see this third-party damage, that's when a regular person gets a little too aggressive with their tools, ruptures a pipe. So these are kind of the different threats we're talking about. That said, let me show you ANAGRAM and how it uses RSC to help risk managers for gas transmission lines design and prioritize mitigation projects. And I'd like to start doing that by looking at a map of assets and risks, which we do on what we call this new project tab or dashboard. And this dashboard allows you to create and view new projects consisting of customized selections of assets and or pre-existing projects. And the projects you create here can be viewed in further dashboards against existing projects, so it permeates throughout the entire model. So look at the large map here in the bottom left. We can alter the key to color the assets in a way that helps us identify candidates for either a new project or the assets in need of review. And right now you'll see MAOP for maximum allowable operating pressure. And what might be more interesting is looking at risk to help us find assets with very large risk. So we can go and change it. You'll see the key automatically updates. But we'll also notice that sometimes pipeline sections are very small. So oftentimes we'll have to zoom in to see the results we want. And so we can do that by picking a portion and zooming in. And now we can see some of these larger values we saw in the key, but couldn't easily see by looking at the map overall. Once I've found an asset or assets of interest, I can click on them. To get more information, you should see the box updated here in the top left. And click a new one in case it had an update. There we go. To get new information about that asset. And then if it looks suitable, I can go ahead and add it to my project, as I've already done with an example over here on the right. And I can continue adding assets either through the map or through more traditional methods with different options here in the top right to create a group of assets that I then create a new project. I'd like to next turn our attention to this compare projects dashboard, and we use this to view or compare metrics across multiple projects. The list of projects may include predefined projects that we load in or new projects that we created from the dashboard I just showed you. I'll also quickly note that in the beginning, I pointed to different threat types that we account for, and Max actually gave a pretty good explanation of this, but just to recap, in this summary table you see below here where we have a mitigation column, these are some of those mitigations in question where REPL stands for replacement, ST is strength test, just to list a couple examples. And so what we'll be going over here is actually this summary table in a little bit more detail. And also the graphs to the bottom and the right show probability distributions that express uncertainty. And we'll be getting to that as well. One other thing I wanted to point out about this summary table is what's special about it, I should say, is that it shows how we break down different risk types. If you see for the different reduction types, we have safety risk reduction, wildfire, environmental, reliability. Alternatively, but it allows us to create a multi-attribute risk score where you can weigh risk differently depending on what type of risk they are, regardless of the units. Moving on to the tables below, we're going to start by looking at risk over project assets. And this is just showing the risk by threat type totaled over all our filtered projects, and we separate into three categories: pre-mitigation, post-mitigation, and the amount of reduction or the difference between them. And at a glance, it's hard to see the largest parts of what we're actually mitigating for this small reduction portion. And we can alleviate that by zooming in to get a clearer look. So now it's much more obvious that, and the order match is actually the key here on the right, that selective seawall corrosion is our largest mitigated threat, followed by manufacturing. And if we're ever not sure for some of these smaller portions, we can of course click and see if the threat, in this case, is weather-related outside forces. So those are some of the tools we have available to us. Moving to the next one, we have probability of event consequence. And it's easiest to understand by explaining the axes and walking through an example. So in this case, the horizontal axis shows that depending on which asset fails, it'll injure a different number of people. The height, where we have marked as probability, tells you how likely that number of people will be injured relative to other consequence levels, with the blue bar, where applicable, always being shorter to show the mitigated probability versus the red bar where it's unmitigated. Now, what this graph tells us then is that in this specific example, we're looking at the threat internal corrosion, the most likely number of people injured during an event is 70. You can see this is by far the largest. But also there is a non-negligible chance that at 524, over here on the far right, there's a chance of that many people being injured. And this is important because it shows that we're able to assess the likelihood of the most extreme events instead of just averages that lose some of these finer details. And because of that, we can use the data to show how we can improve these scenarios. And I'll very quickly note that if you're wondering, why are these probabilities so small? It's because these events are thankfully rare, which means to better prepare, we have to run millions of simulation trials. And we're actually able to handle these simulations thanks to sparse Monte Carlo, and I'll actually allow Sam to later talk in this presentation about that. For the last table, this consequence exceedance probability, you'll notice we have the same horizontal axis, this consequence per event, but are now considering exceedance probability. So for example, if we look at a consequence event of 50, go over here to 50, what we're actually asking is, what's the probability of exceeding more than 50 units of consequence? And so the red line up top at 50 shows that before mitigations, it's 0.003%, whereas the blue line shows us that after mitigation, it's down to 0.001% probability of exceeding more than 50 units of consequence. So again, the likelihood of larger consequences is decreasing, but very much non-negligible. Now, before we dive to the last dashboard I'd like to show you, I want to briefly take a peek behind the curtain of how we make a model like this. And so I have a small demonstration for you here. And so when we're developing a model, we work in influence diagrams that look exactly like this. Within these nodes, we have different blocks of code. So this LOF, COF, all of these have different code inside of them. And the arrows on the diagram help depict the relationship between these nodes, making it clear how the different components interact with each other. We can then evaluate these nodes independently. So for example, this chain of nodes is pointing to this compare projects. And if I evaluate it, you'll notice, although it doesn't have some of the flair, this is actually the same summary table we saw on the last dashboard. So that's just to give you a little peek of what it takes or what goes into making something like ANAGRAM and the language we use. So as I said, I have one more dashboard I want to show you. That's this select projects. And this dashboard provides a way to roll up projects into what we call a portfolio, which is just a group of projects. I find it easiest to understand this dashboard by first looking at the graph. And Max gave brief information on this, but I'll do a tiny bit of recap. The graph plots the projects, prioritizing by default those that are the most efficient in terms of RSE, and that's represented by the slope. These most efficient projects to the left of the budget line are the projects that will be included in your portfolio. Above the graph, you can see a summary of your portfolio with an averaged RSE value as it works in progress. However, most efficient may not always be what you need. Sometimes you may have outside information that says a certain project is better than it may look here or is required for other reasons. And so to account for this, we allow the user to forcibly include projects. So for example, you'll see this project 573 is just to the right of the budget line. It's not in our current portfolio. But what we can do is we say this actually has to be included, and I'll sort this table by RSE so it matches the order we see here. I could go to 573 and say forcibly included, and you'll see the graph update and also our portfolio summary. And although the slope is much less steep than say project 310 that was our most efficient, we are now forcibly including it using our outside information of the tool to give the overall product we need. That said, this concludes my demo portion of today's presentation. So I believe I can now pass off to our next presenter. Thank you.
Thanks,
Ben.
I'm going to hand over now to Sam Savage. Sam, you look like you're in your beautiful backyard.
Thank you. I am, because there is a jackhammer in my front yard. And let's see, I'm trying to share my screen. Do I have permission to share?
Yes, you do. There you go.
Interesting. It didn't let me share sound, however. Just a sec. Stop. Let me just try that again. No. Okay. Click. No. So we won't have sound. You'll have to. You'll imagine the sounds when I get to them. So let me start with this. I'm going to talk about the arithmetic of uncertainty. And the first thing I have to say is it's definitely more complicated than either Max or Ben let on. And the first thing is risk is not just the likelihood of a failure times the consequence of a failure. If it were, then 1 chance in 10 of killing one person would be equivalent to 1 chance in 79 billion of killing everyone on Earth. But those are not equivalent risks. And so, the way I look at it is, I do it always with dice. When you roll a die, that's not the equivalent of an average die with 3.5 dots on each side. And we are rolling dice in this project. I am actually involved in the project with ANAGRAM, as I'll explain in a sec. We're not only rolling dice, we're rolling millions of dice. And so I'm going to discuss a quick little RSE curve demo, which is also more complicated than anything's been shown so far. I'm going to discuss SIPs and SIP math. And we had a question about how do we model actually it's really interdependency between projects due to things like seismic effects and so on. And that's done through stochastic libraries or SIPs. I'm going to discuss sparse Monte Carlo, which is how we handle the like up to hundreds of millions of trials. And then I want to briefly discuss Excel versus Analytica. So let's start with the arithmetic of uncertainty. And what I tell people is if I explained what the mathematicians call this, it would cause what I call post-traumatic statistics disorder, or PTSD. So I'm just going to stick with the arithmetic of uncertainty. But everyone should be asking themselves if they understand the concept even. We know about arithmetic. It tells us that x plus y equals z. But with the arithmetic of uncertainty, it says, what do you want z to be? Here are your chances. If you are not providing chances, or if you have no way of calculating chances, you are not doing the arithmetic of uncertainty. You're probably doing the arithmetic of averages. And again, this thing doesn't tell me the chance of getting greater than 4, right, by itself. So let's start with an RSE model. And this is one of the models that we shared with the California Public Utilities Commission in the project that Max mentioned. And I see that Joseph Mitchell is also on, another expert who's been involved in this project, which has been actually quite exciting and fun. So what I'm going to look at here is I'm going to start with the notion of the RSE curve. That is, we're spending money on this axis and we're reducing risk on this axis. I'm going to start with something that looks very similar to what Max and Ben showed. First, we have 2 required projects. So it doesn't matter what our RSE is, we need to take them. See, we're getting less bang for the buck, but we need to take it. This next one is undergrounding wires. And the next one is covering conductors. These are alternate mitigations where you would never do both at once. So, but let's look at this one. So the covering conductors looks pretty good. The undergrounding wires looks pretty good. Let's keep going. Inline inspection of gas pipes, hydrostatic testing of gas pipes. So those we're looking at individual projects. Oh, but now let's look at pairs of projects. Well, if you did undergrounding and covered connectors, that's dumb. Once you've done the undergrounding, this is just a waste of money, and you'd never do that. And in fact, we could run through all pairs. Here are all pairs. Let's get to all triplets. And the key here, which we didn't really show earlier, but we have the capability to do, is that there are portfolio effects. And now what we're looking at, every dot represents some combination of mitigations. And we can see in this case that some of these are stupid. I mean, look at this one here. This combination, we spend this much money, we get this much risk reduction, and that's ridiculous because we could have spent less money and gotten more risk reduction up here. Well, you have to think about putting nails in all these dots and starting over here and wrapping string around them. And the only ones you'd consider doing, this is known as efficient in the engineering sense or Pareto optimal sense, would be those on the outer boundary. Now, what I want to point out about this is this model is available. And if you go to the About page and you click on this thing, it pops up the video of which I'm going to get rid of here. But we did a workshop on March 3rd with the CPUC, and it will take you right to that part of the workshop. All attendees will get links to that workshop, which then has all the models and so on.
Just to say, Mitsu will be sending out an email to everyone that has links for anyone that wants to follow up on this video, which I think is really interesting, or links to other information about other of the topics we've talked about.
And so the next thing I'd like to talk about is what we call SIP math, or SIPs. And this is a risk roll-up model that was created as a design study, actually with PG&E. And there's an article on this. Mitsu is also going to send the link to this model and that article. But let me describe what a SIP is. So a SIP, or stochastic information packet, is what you get if you roll dice 10,000 times or maybe 1,000,000 times and store them in a database. And this is an approach that has been used in insurance and financial engineering. I'm the executive director of a nonprofit, probabilitymanagement.org, which has standardized this approach because it truly lets you do arithmetic with uncertainty and calculate chances. Now, to show how powerful this is, first of all, the idea is mathematically sound, but in about 2010, Excel became powerful enough to do this in native Excel without any macros. So what we're looking at are libraries of SIPs. Oh, here's safety going on here. These are 10,000 trials. We've got safety, we've got financial, we've got reliability. And I'm referring to each one of these SIPs basically just with an index statement that points into the array. And oh, notice the chance that I exceed 120 million in financial damage is 98%. If I make this 140, it's 9%, 130. Well, so I am doing the arithmetic of uncertainty because I have chances. But look at this. I can use a standard Excel filter to just look at, for example, the pipes. Click. So that was an instantaneous 20,000 trials of like 30 assets. I can't even do the math. It's hundreds of thousands of trials. And, now I see there's no chance of exceeding 130. How about exceeding 75? Okay, how about 50? 98%. And all the other assets are being modeled as well. Notice it's completely auditable. So you're looking at trial 1 here. Let's look at trial 9,876, right? And they're all in there. Every trial is in there. So moving on now to sparse Monte Carlo. We had this model. And by the way, this stuff is easy to explain. The hard part is getting anybody to understand it. And I found the best way to get people to understand it, that includes the client, is to build little models to play with. That way we're all talking about the same thing. Okay. And now what we're talking about is, the chance of a pipe blowing up is like 1 in 5 million years. Okay, great. And how many pipes do we have? Let's see, we had 100,000 transmission pipes. Okay, so we have 100,000 things, any one of which can blow up in 5 million years. That's going to take a lot of Monte Carlo trials, hundreds of millions. And so I figured, well, that's impossible. Until I figured out a way to do it. And I will tell you, this is not part of the open standard of the nonprofit. This required a lot of work, and it's got a patent pending on it, but it is hopefully really useful stuff. So okay, so take me to the model. Here's the model. So let's look at a standard Monte Carlo approach. I've got 100 million trials, trial 1 through 100 million. And what happened? Very little These are all zeros. Oh, except on trial 1, 2, 3, 4, 5, 6, 7, we had a consequence of 5, 6, 7, 8. And on trial 40 million, 1, 2, 3, 4, 5, 6, it was 6,432,000. So I remember waking up. I remember the very night I woke up at 3 a.m. saying, wait a minute. One of the people on our board of directors at the nonprofit was Harry Markowitz, who invented modern portfolio theory. He also invented sparse array math, sparse matrix operations. I said, well, why store the 100 million numbers when we only need 4 numbers? The trials and the associated consequences. And this seemed straightforward at first until we tried to implement it. And there are, remember, we have to model the mitigation. So we have to model not just you reduce the severity, but you reduce the likelihood. Now, Joe Mitchell had asked a question about, well, what about seismic activity? So imagine now that this whole stochastic information packet is for one asset, but we could have another one for, let's call it, a fault. This is a seismic fault, okay? And when we look at that, we discover, oh, we've got a Richter 8 happening right there. And what that would have to filter through and do is increase the likelihood on this trial, right, that we get this asset failing. And therefore, that seismic fault flows through all the rest of the model, making things fail in a coherent way. Now let me talk a little bit about Excel versus Analytica. And this was funny because I developed this presentation actually years ago before I even knew Analytica existed. So the pros and cons of spreadsheets. Let's start with the cons. Documentability. Okay, there are 100,000, there are 10,000 formulas in the spreadsheet. How many have been overwritten? Are any of them right? You'll have noticed in Ben's demonstration that Analytica is, I would call it, recursively documentable. At the very top, you have an influence diagram. And when you click on that, you get sub-influence diagrams. And finally, you get code at various places. And you can tie into databases or do all sorts of crazy things within Analytica. So the documentability problem is really bad with spreadsheets, but good with Analytica. Scalability. So the scalability is, we have a transmission line with 100 segments. How do I add one to that or delete one? Analytica is just automatic. You just add another one. But now the real killer of the spreadsheet is what I call hyperscalability, which is I need to add 10 more transmission lines and multiple time periods to this model. That's when it's game over with the spreadsheet. Now, interestingly, the basic idea behind Analytica is something that Max came up with in his doctoral dissertation, I think in the late 70s, right, Max?
Yep.
And it's basically
Not supposed to be dating either of us.
But it's basically, let me define probability management for you. Probability management represents uncertainties as data that obey both the laws of arithmetic and the laws of probability. Well, that's exactly what Analytica does, because it represents uncertainties as vectors of trials. And you can do a vector arithmetic to add them together, and yet you can still determine the chance of anything happening because it's always in a mode of simulation. And then here are the pros of spreadsheets. And I've got sounds on my end. You can't hear. But there are billions of users. And one of the themes of everything we've done is that I like to think of probability as being like electricity, in which most people don't generate their own electricity. And so in this context, one of the things we've done is we've used ANAGRAM as a giant probability power plant. And we'll finish off today after a couple more presentations here. We'll finish off with how you can take that probabilistic electricity and use it in a native spreadsheet to make chance-informed decisions. So I will now pass it, back to Max, and you can pass it to whoever is next.
Well, were you going to show the ANAGRAM spreadsheet now, or we're skipping over that?
Oh, I can do that now. Well, why don't I do it now, and then I can just rest my piece, okay? I'll pop that up. Sure. So, okay, so what you have to think of now is that this model, when you open it, links to a sparse Monte Carlo stochastic library created by ANAGRAM. And my colleague Matthew helped with this. This is using the latest dynamic array formulas in Excel to do insanely fast calculations. This is simulating at this end. So here's our RSE curve, right? And I'm just going to change. I'm going to remove this division. Okay, I'm just going to get rid of that division. Click. I've got a new curve. Let me undo that. Undo, redo. Each of these actions is really doing a virtual million trials.
We have ANAGRAM working on a server and web for individual modelers that can take subsets of the data into a spreadsheet and work in that format. Some of those
this is
10 billion, billion Excel users still have access to it.
Yeah, but this is not. But this ANAGRAM isn't running right now. So this is where we did an ANAGRAM run, and the stochastic library created by ANAGRAM is simply linked to this in the cloud. Yeah. And even Excel is really fast, but Excel would never have the dimensionality to create the library in the first place. So
thanks
Excel,
so much, really appreciate that. We should move on to end this. And actually, Ernest Lever from GTI Energy, would you like to say a few words? Ernest has been involved with us in developing ANAGRAM for some government agencies. Tell us your perspective on this.
Yeah, thank you, Max. GTI has been collaborating and is collaborating with Lumina to integrate RSE into probabilistic risk assessment tools for risk-informed decision support. And as Max mentioned, we have executed projects for the US Department of Transportation Pipeline Hazardous Material Safety Administration, and the projects have been very well received. We're stepping into some very interesting times in the natural gas industry, because with the wide array of carbon reduction strategies and initiatives being implemented across the United States infrastructure, we will have to address many unfamiliar emergent risks as the natural gas storage, transmission, distribution, and end use transitions to the preferred carbon reduction approaches. So risk spend efficiency metrics are essential to evaluate alternate approaches to achieving corporate societal carbon reduction strategies. We will have to evaluate many complex interactions between different infrastructures, and we'll need solid normalization methods to develop coherent policies as we step into a clean energy future. And, this all sounds fairly simple, but it's not, because each context we look at is really a universe of one. And we can go and run a lot of different types of analyses, whether they're Monte Carlo or Bayesian networks. We can get the SIPs, which Sam loves so much, out of them, and we can provide them to Excel. But we have to associate those with very particular contexts. And there are millions of different contexts that you have to look at. So, we at GTI, we view this as an exciting approach, both integrating with ANAGRAM and all its incredible array of very powerful tools, implementing the SIP math in the background so that we can speed things up, and most importantly, having the risk spend efficiency as a normalization method so that we can compare apples to apples across all of the options that we have to achieve specific objectives.
Thanks so much, Ernest. Really appreciate that. Since we're running a little bit short on time, I'm going to jump into the Q&A, really. Let's see. I'm going to show a few takeaways here. I think really this is just kind of a summary of some of the points that you've been hearing about. First of all, the point that risk management isn't just about assessing the risk, it's about what decisions do we make to mitigate risks. And also, in that case, we need to quantify the mitigation costs. We haven't talked a lot about that, but it turns out that estimating costs of mitigation is almost as tricky as quantifying the risks themselves. And as Sam showed with the example in the portfolio, mitigations often interact. So the RSC of one mitigation depends on what other mitigations you put in. So you need to look at it in a portfolio context to figure out what the best combination of mitigations is. And obviously, it's key to quantify the uncertainties. And Sam explained briefly sparse Monte Carlo that it allows us to quickly simulate a problem, even though there's extremely rare failures and you may have hundreds of thousands of assets involved. These are kind of important practical considerations if you're trying to apply this kind of quantitative Monte Carlo approach. And bottom line is RSC we see as providing a clear and effective guide for risk mitigation decisions. I think utilities outside of California and other organizations can learn quite a lot from the experience with the CPUC and what they're doing. So thanks very much. Let's see if we have a few minutes for questions. Mitsu, do you want to?
Yeah, let me share what we've received. Joseph Mitchell, who I believe is with CPUC, has joined us today.
He's not with CPUC. That might have been my misdirection.
No, he's on that. He's on the team with us, but he is from one of the interveners.
Right.
I see.
That,
Okay.
That represents ratepayers. And sadly, we are apparently not able to let him speak for himself, but he mentioned a question on the upper bounds when I was looking at the multi-attribute value function. I think I said those upper bounds are the size of the maximum possible disaster. And he rightly pointed out, well, actually, very unfortunately, it's hard to say what the maximum possible disaster is. And it's possible to have ones that are greater than the quote upper bound, but the mechanism will still handle that.
Well, and we're trying to talk them out of using this approach anyway. I think it's fair to say that.
Yeah. Fair enough, Sam. Yes, we are. Maybe there'll be a later webinar when we can talk about what the new mechanism is. But still, although it'll use a technique like RSC for ranking and prioritizing projects, even if they do decide to change it somewhat. And Joseph, feel free to send a chat if you want to amplify that question at all.
He's chimed in with a couple more. This one was addressed with Sam, and then also James provided some information via text. But James, I don't know if you want to speak to the second question from Joseph. How does your model handle external drivers, such as in the case of seismic drivers?
Yeah, so it's a great point, because these are one of these kind of widespread threats where they impact something like a seismic event will impact the likelihood of failure across lots of different threat types. And so we can model that through conditional probabilities, where I gave the example of a seam weld failure. Might have one likelihood of failure if you don't have a seismic event, and it'll have a different likelihood of a failure if you do have a seismic event. And then we can model those seismic events probabilistically. So you get the combination of being able to look at the uncertainty in the seismic event, and then also the uncertainty in that seismic event's impact on other threat types.
Yeah, thanks so much, James. I should have introduced him. James Milford's the director of consulting at Lumina, and who is spearheading the development of ANAGRAM within Lumina. But I think there's a key point here, which is, a lot of these, when you start to think about in detail, a lot of these risks are correlated or dependent, and that creates a lot of problems. Most existing systems for doing risk management, other than ANAGRAM, tend to treat them as independent, which is mathematically and computationally more convenient. But with the sparse Monte Carlo that Sam has invented, it allows us to treat the dependencies and still be tractable. Any other questions, Mitsu?
Yes, we have one more from Joseph. Appreciate the questions here, Joseph. His question is, what is your proposed licensing and sales model? Who will need to pay for these services? The utilities, Public Utility Commission, or energy safety offices?
Okay, well, maybe I'll address.
We don't really know yet.
Yeah, well, that's what I mean. I will say we've developed this ANAGRAM tool for a particular utility, which unfortunately we can't name right now. And for them, it's free to use throughout their organization, since they supported some of the development work. So that's one of the large California utilities. And
well, free to use the IP.
Yeah.
That is, the patentable parts
Right.
of it. But it's
Right.
quite a bit of work to do this. And I have to say that we did prototype it using SQL and Power BI and duct tape, and it got us just far enough to know it would work. But it never would have worked without Max and his team at Lumina. It takes powerful simulation and data handling capabilities to do this. It's just, don't try it at home. It's very confusing.
And Joseph, we can follow up with more details if you like. Our goal here is not so much to talk about our great tools, but the underlying methodologies here that are generals. Let's see. I think we're at the hour. Are there any other outstanding questions, Mitsu? Because
I do not see others coming in now.
Well, I'd like to thank all of you for attending. Feel free to send comments or questions afterwards if you have any. And thanks to Mitsu Ganley for organizing this meeting. And she'll be sending a follow-up email. I see she's in the chat. She sent out a few links, and she'll be sending a follow-up email for anybody that wants to kind of learn more about any of the various things that we've talked about. Many thanks.